everyone. I'm by names of Katenderoni Magala, and this is Group 41. Yeah, Group 41 specifically has a project called Indoing You through our topic, which is air quality monitoring with ensemble knowledge distillation. So for our keywords are indoor air quality, air pollution, quantum machine learning, graphical attention networks, knowledge distillation, and ensemble learning. Those are, as we know, indoor air quality monitoring. I'll take you through a brief introduction. When we talk about the indoor air quality monitoring, this shows that we are dealing with the quality of air, or we are leveling the pollutants, or we are monitoring the pollutant levels. Yeah, we are monitoring the pollutant levels of each pollutant within a specified room. Going to the next slide, we have the content. Going further to the background, we have background and introduction. So far, indoor air is a critical global issue impacting health, economies, and the environment. As we know that pollution, especially the air pollution, is a critical global issue. Let me say that within the industrial areas, like if there is pollution, it affects so much the health, even the economy, and in the environment. Let me say that within the surrounding area, like the air pollution, it affects the environment. Let me say the human beings that are within the environment, giving an impact on the health of their health towards electricity-based appliances. Electricity-based appliances. This means that in developed countries, they are moving towards getting those items, or like let me say giving an example of an oven. That means that if I buy an oven, I'm shifting to a developed thing from a traditional thing. Remember, in traditional culture, some people used to use most of the people used firewood as their source of fire. But right now, if we are to see, people are just buying gas to improve on the indoor air quality, because we are moving towards the developed generation. However, in the developed regions, the transition is slow, and many continue to use traditional fuels like the fire talked about, resulting in high level of indoor air pollution. Saying that the transition is low, meaning that like going to the developed world, it's quite low, but it's quite challenging because those things are really expensive. So like you can just, a person in rural area can never purchase a gas, but can easily purchase firewood because around their home, like there are very plenty of trees. That's why it's quite slow in transitioning. Going further to the related works specifically, this I can say that what have we so far worked on to improve on the air quality? We have introduced machine learning in AI prediction, AI air quality prediction, like the ML models. Let me say the SVN, AN, and CNN, like LSTM. Improve air quality forecasting by analyzing the spatiotemporal data. However, challenges include data imbalance and computational inefficiency. Remember, when you're dealing with collecting data within we have different pollutants, and there might be data imbalance between them, and computational inefficiency. Computing them, like let me say that, giving an example of this model of quantum feature learning, especially quantum feature learning, like the quantum feature extraction. If it wasn't for the quantum feature extraction to compute that data efficiently, like let me say gathering that raw sensor data and then turning it into the weighted data that is required to proceed to the quantum feature selection, then there would be inefficiency. We go ahead to see ensemble learning for high quality monitoring, ensemble methods like random forests and GB enhancement remember this one deals with linear regression, dealing with specifically uh, what data that are like not classified, that is non-classified, but those that labeling of data. Okay, going further to the quantum machine learning, I've talked about it. Quantum machine techniques such as the BQC, the optimized feature selection, and model convergence. However, hardware limitation restricts large-scale deployment. Going to the recent trends, indoor air quality monitoring is evolving rapidly due to technological advancement in AI, learning, and IoT. New methodologies improve forecasting, real-time monitoring, and decision-making in smart environments. Let me say that using the quantum machine learning. This one has enhanced circuits, processing the highly dimensional sensor data efficiency, and improves early warning systems for air pollution. Here we shall have like it will process the highly dimensional sensor data and then specifically improves the early warning systems for air pollution. Let me say that we have a system already that is to monitor whether the levels of carbon dioxide are rising or like are low. So when this system is triggered by the pollutant level being high, then it gives an early warning. We have the graphical attention networks, we have the knowledge distillation, which transfers knowledge from a large model to smaller, efficient models. Specifically, knowledge distillation here, we deal specifically with teacher model and the student model. The teacher model is always the large ML model that transfers large sum of data into like breaks it down into smaller, so that it can be learned by the student model. In the ensemble learning techniques, we have the random forest, boost. Other emerging trends in IA quality monitoring, we have the multimodal data fusion for privacy preserving monitoring, energy efficiency, IA quality using the tiny ML frameworks, hybrid quantum classical IAQ models, yeah, and many others. Going further to the literature review, here specifically we deal with the crucial factors. We see the crucial factors, we see all the suffering of like how methods have been suffering from the sensor drifts, environmental noise, highly maintenance costs, and limited scalability. Highly maintained costs, let me say that we have a model. Okay, we have sensors. Yeah, sensors. Now, these sensors, purchasing those sensors and then maintaining them to see whether they function very well, they will require a lot of costs. Let me say the sensor drifts. Let me say that they're collecting like imbalanced data, environmental noise, limited scalability, like purchasing those sensors. Sometimes you can find that like in Uganda, let me say in Uganda, you can never find a sense of PM 2.5 or PM 10. So you have to go abroad and then get it. Those are some of the all the challenges within these methods. Then we have with advancements in artificial intelligence, machine learning, Internet of Things, and quantum computing. IAQ monitoring has evolved significantly, enabling real-time, accurate, and scalability air quality predictions. So right now, like we have evolved significantly since has been some improvements in this IAQ monitoring, especially dealing with the ML stuff, ML models, artificial intelligence, IoT things. They have nowadays become accurate, they're able to monitor the real-time data, scalable, in air quality prediction. The evolution of IAQ monitoring from traditional sensor-based method to AI-driven intelligent system has improved forecasting accuracy and real-time decision-making. What I've just talked about. However, challenges such as the sensor reliability and data privacy and computational efficiency remain. Future research should focus on hybrid AI, quantum models, self-learning systems, and lightweighting. Yeah, going further, we have the problem statement. When we say that we have specifically the domain application problems and computational problems. When we talk about the domain application problems, how has this air pollution affected the environment? So here we have the prevalence in air pollution due to poor ventilation. Most rooms or most houses have poor ventilation. Emission from the households. You find someone cooking using firewood and there is poor ventilation or emission from household, like the smoke is cooking within the house and the smoke is too much and there is poor ventilation. That will automatically lead to bad air quality, or like, let me say, pollution within the house, then leading to affecting the what? Affecting the life of the person or the health of the person. This necessitates a robust IAQ monitoring system. Existing solutions lack predictive capabilities, limiting timely interventions. We also have the computation problems. Computation problems, this is whereby how has indoor air population affected the computational part, like the IT part specifically. There are several computational challenges. High dimension data processing. Let me say that we have a lot of data. Sensor data from multiple sources require efficient feature extraction and representation. As I told you, that feature extraction means like extracting data, like a large sum of data, especially raw data, and then transforming them into weighted data that is able to be significantly used by the model to predict or monitor the IA quality. Let me say the limited labeled data. IAQ monitoring requires extensive labeled data sets, but data collection is often expensive and time consuming. It's often expensive and time consuming. Limited, yeah. Time consuming means that you always need to be checking out, are the sensors working? Like, are they collecting like, the good data that we need, or are there some errors? Is it diverting from what we want? You have to be checking on it every time and then, like the data set. What is it really connect? Then the often expensive. That means that getting this kind of data is quite expensive. First of all, buying the sensor is quite expensive. Spatial and temporary dependencies. Air quality varies over time and space, requiring models that account for these dependencies. Model complexity and efficiency. Some models are complex. Thank you very much. Let me allow the next participant to present.
Thank you very much. Good evening, everyone. My name is Nantongo Jocelyn Madrin, and I'm going to start with our methodology. As you see it in the diagram, it's our methodology, and it shows that the machine learning workflow for air quality monitoring, covering data collection from the IoT sensors, preprocessing, explanatory data analysis, model development, evaluation, and section. So the key steps include feature selection, statistical analysis, hyperparameter tuning, and advanced modeling techniques like quantum machine learning and ensemble learning. When we continue to slide 11, here we are going to talk about the next slide. The next slide, we are going to talk about the dataset description, and basically our dataset was sourced from GitHub, and it contains data collected from various sensors that are monitoring air quality and environmental conditions within a specific location and environment. The dataset is organized with features such as TS, carbon dioxide, humidity, PM10, PM2.5, and temperature. the PM10 and PM2.5, particulate matter indicating air pollution levels, and then the VOX, volatile organic compounds that can be harmful, and then carbon dioxide levels as an air quality indicator. And then we have temperature and humidity, that's the environmental conditions affecting air quality. Timestamp and date or time, it records the exact moment of data collection. So this data enables real-time indoor air quality monitoring for improved health and environmental safety. When we continue to the next slide, the next slide is going to talk about our output or the expected results and discussions. So after running our EDA code, these are the results, some of the results we got. We have the carbon dioxide levels that fluctuate over time. We also have concentration of PM10 particles over time. Down here we have the presence of PM2.5 particles. So it shows the concentration of PM2.5 particles. And then the next figure, it represents the fluctuation of humidity levels over time. When we continue, these are specific outputs for each and different model we aimed at getting the accuracy, precision, recall, and F1 score. So these are our different models. They are 10 in number, and that's the accuracy. For example, CNN, that's its accuracy, the precision, the recall, and the F1 score. And then for this table model evaluation, this one was basically for the ensemble learning model, where we assembled two models. That's the LSTM and the NSTM model. That's the MSE, the F1 score, and the precision. And then after the ensemble, the final output, like after assembling both of them. Then when we continue, still for our models, we present to you the training rate, the training time, and the learning rates separately, and also show you the summary statistics we got from our explanatory data analysis visualization and dataset visualization. When we continue, this is we go to the conclusions and limitations, and some of our limitations experienced a notable lack of source identification studies was found in environments such as airports, train and metro stations, hospitals, and museums. Also, scarcity of studies in low and middle income countries, especially in Africa, was observed. PM2.5 and PM10 were the most studied indoor pollutants for source appointment studies, followed by VOX. And also leading to real-time source identification, enabling the implementation of reactive mitigation measures. When we go to the conclusion, we see that the present study is aimed to critically review the recent advancements in indoor air quality monitoring and source identification to better implement relevant mitigation measures. The most frequently monitored indoor environments were homes and schools, and the source identification results found sources of both indoor and outdoor origins, with many studies estimating major contributions from indoor sources. And these studies conducted source apportionment for cooking and heating in rural houses. So when we continue to the next steps here, we are saying that the things we are going to do. So we are going to have enhanced feature engineering, and here we shall have to identify and integrate new relevant features, normalize and standardize data for better consistency, and then advanced model training. Here there is experiment with diverse algorithms, perform cross-validation for robust generalization. Then we go to optimized hyperparameters. Here we shall use grid search, random search, and Bayes optimization. Fine-tune hyperparameters for optimal performance. Then there is continuous monitoring and training. Here we implement real-time performance monitoring and also set up automated alerts for anomalies and data drift. And then we also have effective visualization and reporting, where we shall develop intuitive dashboards and also generate comprehensive reports, and these will be used for stakeholders. When we continue to the next slide, it's talking about some of the references that are in our concept paper. These are some of the references we got, and there are 10. And lastly, acknowledgement. We would like to express our sincere gratitude to Mr. Galiwango Marvin, our advisor, for his continuous support